Welcome to Impact Quantum, the podcast for the quantum curious and the entangled enthusiast alike. Today, we're diving deep into the fascinating world where theoretical physics meets real-world engineering with none other than Marouane Salhi, physicist and CEO of Qubit Engineering. Forget Schrödinger's cat, we're talking about the kind of quantum that optimizes wind farms and power grids, not feline survival probabilities. Marouane shares how his team is tackling massive engineering challenges using quantum-inspired approaches, all without needing a working quantum computer, yet. From turbine layouts to toggling thousands of grid switches like it's a game of high-stakes Tetris, this episode is proof that sometimes the most boring problems are where the real innovation happens. So if you've ever wondered how quantum computing is quietly reshaping our infrastructure, this one's for you. Let's jump in.
Hello and welcome back to Impact Quantum, a podcast for the quantum curious. And with me today is the most quantum curious person I know, Candace Kahuli. How's it going, Candace?
It's good. It's good. Thank you so much. I'm so happy to be back and happy to talk to our guest today.
That's good to see you back in the studio, and we have a really interesting guest today, Marouane Salhi, who is a physicist, and he's also the CEO and co-founder of Qubit Engineering. And I love the tagline that they have. It says, "Harnessing the power of the quantum realm." Getting a very distinct Ant-Man and the Wasp kind of vibe from that. And judging by the look on your face, I'm not the first person to say that. In the virtual green room, we talked about some of your work, and you've lived in Maryland for a time. So tell us about yourself. Welcome to the show.
Yeah, thank you. Thanks for the invite, Frank. Happy to join you, Candace here. So I am a physicist. I'm a computational physicist / theoretical. I did my interest in quantum physics, actually in quantum computing to be precise, started early on. But we only saw the availability of quantum computing machines, quantum machines, only in the last few years. To be kind of precise, that's when you can actually have you have actual access to play with the machine and test it. So a quantum physicist would focus on quantum optimization. I am also the CEO and co-founder of Qubit Engineering, an optimization startup for quantum formulating to formulate problems in engineering in a way that we can run it on actual quantum computers. I co-founded Qubit Engineering with my colleague George, who's also a physicist. He's also a professor at University of Tennessee in quantum information science. And also our third co-founder is Hatton. He's an engineer. We kind of got him into working with us and helping us in building our software for quantum applications.
Very cool. Very cool. I just have a lot of questions because there was what types of engineering problems have you or are the most popular? I've just wondered about that.
That's a good question. So I would say it's not about how popular, it's about finding the right use case.
Interesting.
A lot of effort in the community is to identify which problem can benefit from quantum computing, from quantum algorithms, from quantum optimization, that we can see advantage over classical methods, over classical approaches. So, and that's also how we looked at it. We looked at we in fact, as I said, we're not engineers to start with, but we are physicists working in the engineering now industry. And the first thing that we started thinking of, okay, what kind of problems can we solve? What kind of problems can we see real impact or quick impact or the low-hanging fruit kind of we can capture using quantum optimization approaches? And the answer comes from a mathematical, it's purely mathematical. So we needed to understand the type of problems that have interest in the engineering industry have an impact, but also something that the quantum optimization can contribute to. And the answer for us is not only for us, but the answer for is basically any problem, any engineering problem that we can represent as a network of nodes and edges. For people who are familiar with the quantum annealer machine, the wave, try to think of this the topology of the D-wave machine. It's built of qubits and connections. So you need to find a problem that cannot be mapped into that. And you'll be surprised in our engineering world how many problems are. And one of the problems, the first problem that we started working with is the design of wind farms, wind farm layout optimization. Yes, and maybe you don't see it that way, but let me kind of hint into that. Turbines in a wind farm. If you look at a wind farm, so actual turbines, you can think of them as nodes, and then the wake interaction between any two turbines, you can think of it as the edge connecting them. And that changes based on the relative position of these turbines. Depends on the distances, depends on their altitude. So it's actually physically, if you look at it from a physics perspective, it's a perfect network of what we call a fully connected system that matches, the type of problem you're looking for. And that was a choice. That's how we selected the first use case. And
interesting. I would not have thought that. I mean, it makes sense now that you say it, like turbulence and things like that. Because these windmills are massive. Like I mean, I've never been less than maybe a mile or two from them, and they're just massive. Like and I would imagine, I mean, they're like airplane wings, basically, right? I mean,
yeah. So I mean, the hub altitude, the altitude of the hub, the center of the turbine, where the actual blades are rotating. I mean, it can go up to 120, 140 meters.
wow.
I think the big ones. So the actual diameter of turbines, the big ones, I think they can go to 160. I think that's the biggest we've seen. So they can be really, really huge. Again, the way we look at it, it doesn't matter their size. From a study perspective, they are a point or in a network. Of course, we associate with that particular, and let me say, not a point, but a variable in our system. But that particular variable is associated with a power generation. It's associated with altitude, exact position. It's associated with wake effect it's causing. And it's also submitted to, or kind of feeling the wake of other generated by other turbines around.
Interesting. How specifically do quantum computers help with that in ways that, a classical computer wouldn't? Like, what is it? Is it just a good old fashioned optimization you're trying to find? Is that what it is?
So let me step back a little bit. What we are solving, we're solving challenging optimization problems, which are, as I said, are built in the form of the network of nodes and edges. And what this does to the problem, it creates almost an infinite search space of possibilities. You have, so the best example, we can give a good example would be if you have a room with 100 seats and you have 50 guests and you're trying to distribute these guests, there is almost an infinite number of possibilities. The exact number would be 10 to the 31.
Oh, wow. Okay.
If you want, and we did actually this calculation with our with a collaborator from the supercomputer at Oak Ridge National Lab. and we said, if you want to do a brute force and consider all possibilities, how much time would we need using your supercomputer? At that time was Titan, which is, I think at that point was maybe the first or the second fastest supercomputer in the world. This is just a few years ago, and the answer was around 31 years. I think with the new machine available at RNL now, Frontier, it's probably maybe 30 years or something. I don't know that, but it's so that's how rich this type of problems. Now and that's why quantum computing can make a huge impact in the future, because it can navigate this space not through trials of looking at every single possibility, but just by literally zooming in through that space and finding the optimum configuration.
Interesting. I mean, how long? What's the time on a quantum computer to compute?
So on a quantum computer, this problem is like in microseconds. It's very physical, but this problem of 100 from and this is it's not from an engineering perspective very interesting. It's simple.
It's also kind of boring, it's not like
correct,
we're going to change the world. We're going to do this. We're going to break encryption. We're going to cure cancer, map all the protein folds and whatnot, right? Like it's pretty, to be blunt, basic, but you know what? But boring is where the money is, right? Like there's a lot of these financial gurus, and like the more boring something is, the less competition is going to be. And like, I don't want to go down that rabbit hole, but like, I mean, it sounds like, boring tends to pay the bills, right?
That's a good point what you're saying. In fact, in general, industry only care about what kind of advantage you can provide them. It doesn't matter whether you're using a quantum computer or a simple Excel sheet. This is the reality. But of course, we will reach a point where sophisticated or basic tools are not the solution, and even some sophisticated classical methods cannot even cut through. And that's why you need to start thinking about new innovative approaches. And what we really do, and the way I look at what I'm doing for over the last few years, is bridging the gap between some interesting tools that are mainly used in research that usually engineers are not trained to use them, and bring them back to the engineering and say, hey, using these tools, we can get this serious advantage. In fact, we've been doing this. As I said, our first use case was in the wind farm. When we started working on this, and we did not start on our own, we started collaborating with actual wind engineers, with actual wind farm developers, big companies, different companies from almost everywhere. The first thing I say, you guys, you're not wind engineers. What are you doing here? What's the purpose here? And say, hey, we have some cool tools for optimization, and we want to test them with you guys and want to see how this. And then after a couple of weeks, once we exchange the data and show them the results, they are basically, now they want to know more. How did you do this? And why are you getting so? And then actually, even they get surprised with the results we can capture. They say, hey, we want to do this test again. We think, it almost seems like a little bit, you got lucky on this one. Let's try again. Let's change the problem. Let's increase the size a little bit. But it's not magic or Sonia. It's basically a new way of solving a problem that they've been using the same method for the last 3-4 decades. Now, I'll give a simple example. When it comes to the wind farm layout optimization, the way it's done, basically there is a program software, few commercial ones. Sometimes some developers develop their own internal system, and the way it starts, they basically pick the lands, they have all the data required for the project, and then they start from a random design, just random one. And the way they do it, they basically start moving one turbine at a time from one location to the other, while watching how the energy field is changing, going up and down. And of course, this goes through an iterative process, as long as possible until they see that there is no more progress. Then they stop the calculation, this numerical search, and they say, we got it. This is the best we can do. We don't do that. The way we do it is basically by selecting the position or selecting configuration from thousands of possibilities, just like the selection of where to place your guests in the room, 50 guests in 100 rooms. We generate thousands of potential sites for the turbines, and then we select the exact number that we want. The advantage here is that you're selecting one coherent configuration rather than moving one turbine, which will impact, maybe it will improve the production of one, basically ease up a little bit on the weight for one turbine, but maybe it will increase the weight on another one, and which is an iterative process. So it's a very different approach. It's a combinatorial optimization, which is what quantum computers are meant to. And we started talking about quantum, and maybe I should hint to this. We've been doing. We started using quantum annealing machine. We built our main system using quantum annealing machine, or for quantum annealing machine, and slowly we shifted a little bit to using. Slowly we shifted to using simulators, or what we call quantum-inspired solvers. I believe this this name, quantum-inspired solvers or quantum-inspired optimization, was introduced first by Microsoft Azure Quantum. They were pushing for it, and today it's the way to go to support the development of new quantum applications. So the challenge for quantum engineers or quantum application engineers is that they've been trying to map some large complex engineering problem into a quantum machine that is very limited in number of qubits, in number of connectivity, in the that's subject to noise and errors and so on, and that actually impacted a little bit. So that shifted the focus from developing the application to trying to match your application with the current hardware. If we fast forward in the future and we'll have the best quantum computer, then we will never worry as a quantum application engineer. You will not worry about the machine. You'll just worry and focus on developing your problem, on developing your application. So today, the engineer is divided between not only trying to rethink his problem to map it into a quantum machine, but also worrying about the capacity of the machine that he'd be running his problem with. So this was kind of clear to us, and the opportunity of shifting towards these quantum-inspired solvers. What it does first, it actually let you focus on the application rather than on the limitation of resources, rather than on limitation of the number of qubits and of connectivity. You can ask me and say, oh, well, you can build the problem however you want and build your application, but yes, it's not going to run the same way if it's running on a quantum computer versus running on a classical CPU and GPU machine. That's true, but we don't have that machine yet. And another very interesting point is that what we realized by rethinking the problem, we're actually saving a lot of this search space. We're simplifying a little bit this huge search space, which is allowing us to achieve and get better solution than classical approaches. When you are selecting a full configuration of a wind farm, you have more chance to get a better solution than iterating on moving one turbine at a time based on whatever resolution you have based on, doesn't matter the number of iteration you do, you will be stuck in local minima. Definitely, you'll be struggling there. So yes, this quantum formulated wind farm layout optimization problem is not running on the actual quantum machine, but it's running on a solver that's behaving or trying to behave like a quantum machine, and we still get significant advantage. So this is something we've been advocating for, and we think this is the lowest hanging fruit, and it is clear today that there is a big shift or there is a serious consideration to quantum-inspired optimization. And this is in fact, if we want to say the priorities today are as follow, or what can you possibly do? The best thing you can do is to develop applications for quantum-inspired solvers, one. The next step, which we're not there yet, a lot of companies are looking at this, is running a problem on a hybrid system. Classical, basically a system made of classical computer and quantum computer. The next level would be running it fully on the quantum computer. I believe even running on a hybrid system, a classical / quantum, we are still struggling there because we're not really sure how to decompose the problem between the CPU and the QPU. How can we divide our optimization problem between?
It's interesting you say that, because a lot of people will kind of scoff at simulated quantum machines. What's your thought on that sort of debate, or is it kind of just one of those silly debates that people like to get into?
So I'm focusing on simulated quantum optimization, simulated solvers for quadratic and constrained binary optimization, or quadratic constrained binary optimization, or even if we consider polynomial problems, not just quadratic. Now, I would say, if we're talking about general simulating a quantum physics system, that's a different story. Simulating a molecule, there is nothing better than actual qubits to simulate molecules. And that particular discussion, it's very it's clear that a quantum system is it's better. The challenge there again is how big of a molecule can you simulate today on a quantum computer? If you want to do that on a classical computer, I mean, people have been doing this for decades now. People are studying molecular dynamics and just trying to simulate the quantum physics of molecules and atoms. They've been doing a lot of good job, and a lot of applications and a lot of simulators have been built for that. And their main challenge is that every time they need more and more bigger machines, because it doesn't scale up, the same way as a quantum system.
Right.
When it comes to so that's what mostly used, simulating on a quantum computer for when it comes to material science. I think quantum systems would be the best, and some sophisticated high performance computing kind of modules have shown very, very good results, and they made a lot of good progress there, but they're still very expensive computationally. In fact, the impact, one of the most expected impacts of quantum computing in the industry is in the pharmacology, designing new drugs, designing new molecules, and so on.
Right.
Biochemistry and all that. what we are working on in terms of simulation is purely mathematical. In terms we are mapping engineering problems, formulating them mathematically in a way that we can solve them on these solvers, on these quantum inspired solvers. So these are two different kind of fields. So when you're trying to simulate the quantum physics system, you better simulate that on an actual quantum computer. That definitely, it's more natural. But we are taking an engineering problem, which like went from design, and then now trying to optimize it and simulate it. In fact, what we do simulate the interaction. We take the whole problem, the whole dynamics of the neutron, and map it into this network of qubits. And we basically, literally match every turbine with an actual qubit and the different interaction that it has with the other qubits, everything. So we're kind of simulating that. But as I said, the challenge is the machine, the size of the machine, the number of qubits, the number of connectivity you can have, and so on.
Right.
Does this make sense? Yeah, go ahead.
So I'm going to take us a little bit away from this for a moment to speak to some of the, the interests and concerns of audience members. So I'm going to ask you, so for someone looking to get involved in the quantum computing field, whether as a student, a developer, or an investor, what's the most unexpected piece of advice you would offer? I mean, your experience is quite extensive, and the way you talk about everything, I mean, clearly you've got the skills involved. So what skills do you believe will be the most valuable in this rapidly evolving landscape?
That's a very, very good question. And I have to say this, let me just point something. There are a lot of people are working on different things when it comes to quantum computing, from the hardware to the software to the error corrections, and everyone is contributing from its own position. There are two ways to be part of this game, this part of this development, the technology development of quantum. Whether you're looking at contributing to it at an earlier stage or in the long run, I believe the investors who are involved in developing, in investing in quantum hardware, they have the long-term vision where they say, hey, we want to contribute to building this fabulous machine, these sophisticated machines, but it takes time. And they look at it that way, they understand it. And even, as we move forward, we will, right now, the space is divided in superconducting, photonics, I don't know,
CAD qubits, ion
Ion
traps,
capture.
yeah.
Exactly.
All kind of qubits. At some point, we will see some kind of preference and say, oh, actually, the winner is whatever it is. From starting from superconducting to ion traps to neutral atoms to whatever you want to call it, photonics.
Right.
But it's part of investing and so on. It's part of the vision and the risks that people do, and I think we're all learning from. We're learning what is happening from the ion trap side. We're looking from the superconducting, from the photonics. So it's nothing is wasted. Everything is useful, and we're learning from. Now, if you look at it from the perspective of an engineer who's trying to be involved, this depends. If they want to be part of the hardware, it's different than if they want to be part of the software. I believe there are efforts that will be limited in time. I mean, at some point, let's say Microsoft, the Marouane, the new topologically protected qubit will be an actual reality. And we'll have much better qubits than a lot of the work that we've done so far in some of these noise reduction, error correction, all that. maybe we don't need that anymore. So I think as I said, it depends. So you need to choose what you want to play now. You want to be part of you want to contribute now early. This is what we need today. This is what we're trying to understand. Or you want to be part of the future in terms of long term. And I don't think there is one answer for all of them, whether for investors, whether for engineers, whether for entrepreneurs. It depends how you look at it. Let me share the way we looked at it. We looked at problems that are coming from the engineering. In fact, I still remember my first presentation at the IEEE Quantum Week when I said we're looking at an energy problem using quantum simulation. The first and natural reaction was like, we're still talking about atoms and molecules, and you're talking about energy. I mean, today we're working on power grid. We moved from turbines, so we progressed. Like, I don't know what they would say to me if I say, hey, I'm trying to solve power grid management optimization today. But the idea is that you want to look at it differently. It's what we are doing is we are mapping the mathematical dynamics or physics dynamics into a theoretical model. It doesn't have to be a molecule, doesn't have to be atoms. It's a pure optimization problem.
Right.
What it does, it gives us access to some solutions. Let's call it configurations. Let me give another example that we've been working on for the last 3 years now. I started with the wind as an example. We're still working a little bit on the wind, but the focus right now is on power grid management for many reasons. But the grid, sorry, I lost it. Going from there is this idea of finding a problem that has a specific mathematical structure where you can access a solution that you cannot access sophisticated is feasible through this new way of solving problems, this discrete combinatorial optimization. Let's call it quantum combinatorial optimization. The idea, why we want to solve combinatorial problems using quantum computing. So quantum computers are qubits. They actually embed this idea of having all possibilities at the same time through superposition. It's almost like packaging all possibilities in fewer variables, fewer smaller systems, and they can navigate through very fast. And that's why they offer an opportunity to solve these problems that from a classical engineer, when I mean classical, I mean using classical methods, who's trying to avoid what they call the combinatorial explosion. It's literally, they say, hey, the number of possibilities is exponential. I can't deal with this. Yes, of course. That's why you need to change your approach. Now, going back to where I started, I said, the way we look at it, we saw that there is an opportunity in engineering where we can map some of these exponentially growing, in fact, the correct term of using it called NP-hard problems. We can navigate the space slightly better and faster to get results or solutions we cannot get before. And in fact, we learn from it. In fact, that's why right now, for example, we're solving large scale problems in this discrete space, which wasn't very clear, wasn't very intuitive to many scientists or engineers at the beginning when we suggested this approach. Let me connect another example. So I mentioned the grid. You can think that the grid is a very large infrastructure. It's very important. It's critical. The way
the power
we
grid,
look at
to be
the
specific,
power
is
grid.
what you're
Sorry,
referring to.
yes, the electric power grid. The electric power grid. The way we look at it through our algorithms, if I may to simplify this way, it's a bunch of switches that you have. maybe thousands, tens of thousands, and you're trying to find which one to keep on, which one to turn on. It's again another combinatorial optimization problem. And for that, you cannot do it the classical way. You cannot do brute force. You cannot do classical where you try one at a time. You need to have a little bit more sophisticated approach. And quantum, as I said, people always expected that the quantum computing contribution is only coming from the hardware. What we learned over the years, no, it's also coming from the way that the new way of thinking of the problem. We look at it differently. We're solving now a network of nodes with branches, different biases, different coupling.
I see what you mean. So quantum-inspired algorithms also play into this.
In fact, I believe now the DOE Office of Science, at least they showed in a last presentation I attended that they're prioritizing now quantum-inspired optimization, then hybrid quantum computing, then quantum computing, then the actual quantum algorithms. So this is the first time I saw it. In fact, I took a picture of it. I was so excited to see that they kind of got the message in a way. And as I said, you need people to invest in the quantum hardware. You need people to work on developing the machines, and which is a long-term kind of things. But you need also to be ready by getting a community of quantum engineers developing new applications. And the main motivation is, we're not just building the application to be used when the quantum computer is ready. No, we can use it, and they are actually offering as an advantage today.
Right.
And even more in the future when the quantum hardware will be ready. So this is honestly stepping back a little bit out of the hype that people talk with the quantum and say to some extent, okay, in the next year or 2 or 3 we're getting a quantum hardware. No, we don't know that, but we can actually do something useful. We can rethink our problems. We can rethink our algorithms and have an impact today. And also we will saving time by bridging and connecting some engineering problems like the one we are doing at Qubit, engineering energy problems that people never thought that we can actually cast them and project them into a formula that can run on quantum computer. So if you ask me what we do, our core expertise is in the quantum formulation of the problem, this combinatorial optimization, which involves a significant domain expertise. You need to understand really well the application. You need also to understand how to build your quantum formulation of the problem. So of course there's a debate. You say you're running it on classical systems. Why you want to call it quantum? I would say yes, it's running today on a classical systems. It's generating better results than the classical approaches that been developed for the last 2-3 decades. But also it can run on a quantum computer if you give me one now, and you will not be able to match the results that I would get out of it. So,
interesting. Very interesting.
Okay, so let me ask you this. Looking further out, let's say 10 to 15 years from now, what's one moonshot application of quantum computing that you personally find the most exciting or transformative? Even if it seems speculative today, what fundamental breakthroughs would be required to make that a reality?
So that's of course very good and very hard questions, but I'll try. Yes. I believe our next challenge is to understand how we can connect classical computers with quantum computers. How can we divide? So this is a more general kind of concept in the sense that I think hybrid quantum computing will be our next challenge for the next 10 to 15 years. And in fact, we see it as a continuation of developing applications and running quantum applications on a simulator. So the simulator right now is limited to CPU. Soon, once we have a better idea how to incorporate part of the calculation on the quantum while running it on the classical system, that's going to be the next. That's the next. That will have a very serious impact. In fact, in the future, it's not going to be purely quantum, even in 30 years, when we have a very good computer. I believe this idea of running classical and quantum computer at the same time is the winning course. We're not going to be able, we need to even rethink the problem now even more, in the sense that where and how to connect classical and quantum computers when it comes to our optimizations. Now, for the applications and the use cases, this is what in 10, 15 years, I think whatever applications we are doing today, whatever use cases we are developing today will continue and will get even better. And that's why we need to start now.
No, actually, not to interrupt you, but like I think I want to click on starting now, like the importance of starting now, because I think there's a lot of people, and you're a trained physicist, right? And you even said, like, you know, you're not primarily an engineer. So what could people who are not physicists do, like software engineers, AI engineer? Like, I mean, because I think that's really one of the people ask me about this a lot. Like, what do I think about what they should do about quantum computing? I was like, well, one, if you're in the C-suite or in a corner office, you should really start thinking about being ready for post-quantum encryption, right? That's kind of the first thing, right? I used to be an EMT, right? And the first thing is you remove the body from the burning vehicle before you start treating it, right? But I think the second thing is, in terms of career projections, I tell people just get used to it, right? Just get used to the concepts, right? Get ready, because a lot of what traditional computer science people, myself included, we kind of have to unlearn what we've learned in a very real way. It's not that I have to throw out everything, but I kind of have to stop and think a little differently. Am I on target with that? Am I off base? What do you think?
I would say we are we're moving forward by being a little bit more interdisciplinary and to some extent complementary.
Right.
I think every different kind of engineer, they build certain way of reasoning, and they are used to some kind of input, some kind of output, and a process in the middle. Right now, you're talking about a different dynamics, slightly different engineering, quantum engineering.
Mm-hmm.
So you need to be comfortable a little bit understanding the dynamics of it. And I wouldn't say throw, absolutely not, but it's more adding on top of it. That you could be a computer science and you have a background and you have a good clear understanding of how to write programs or softwares in classical way. Now you need to learn some new skills when it comes to it. And again, I don't think moving forward, what the way I see the workforce will be, we will need to be able to build teams that are complementary. We're not expecting one person to know everything or to totally go from computer science to quantum computing, but we want him to be able to work with quantum physicists to connect the dots and to basically have that flexibility and that understanding of communicating with other colleagues doing that and using their language and so on, and even building something together with them. That's the idea. So we are moving slowly towards an interdisciplinary kind of teams that where the engineering is getting, and of course it depends on the application, it depends on what you're building, but it's getting more and more intertwined, and you need collective efforts. You know, even in computer science or in software engineering, you have people say, "Hey, I'm a front end developer. Hey, I'm a back end
Right.
developer. I'm you know,
Oh, full stack, right?
full
Yeah,
stack." Here we go. So I think this way. So I don't see a problem. I don't see it as a challenge. Oh, you need to shift. You need to unlearn. Absolutely not. No, you need to continue and build on top of it. And I don't think even there is this concept of unlearning anything. I think we only can keep learning something and then kind of.
right.
You know,
Maybe the better way to phrase it is drop assumptions.
yeah. You know, so let me bring. So I know this is too abstract, but let me put this. I think there are, as we're moving forward, the quantum industry is getting better at identifying its main challenge.
Mhm.
It's getting better at understanding what use cases they can build, what kind of skill you need. In fact, for what we do, optimization. And, I have to be careful right now, even because when we say quantum optimization, I mean, as I said, the debate whether you're running on a quantum computer. Yes, we did run on the quantum and a linear YD wave. Yes, as a physicist, I loved running on actual quantum machine because you especially when you have access to the different knobs and you see how the output is changing and how it's very exciting but now what I'm trying to, if there is the message I want to say is that we're not, we need to have a combination of the skills when it comes to the application, the domain expertise, and you need to have that quantum. So having it in one person, sometimes it's hard. But working in a group, in a team, that's where you can build something. In fact, that's for our team. That was the reason we started working in the energy space, because it's physics and we understand the physics. And then we have the background in the quantum computing. Then we can solve the problem. I mean, let's point out the elephant. I mean, quantum optimization now, the financial market, all of the portfolio optimization effort. A lot of companies are trying to solve this problem. And one of the main challenges is that you need one guy who is really experts in the actual problem in finance and understanding how the market goes and what parameters really have influence versus others. And you need to have someone who can formulate that problem and so on. So combining these two expertise is, I think, the way for a successful development of a solution. Of course, what happens here is that either you have people who've been doing this in a classical way, they're trying now to understand the quantum computing and try to implement what they learned there, or the other way, you have quantum computing experts who are trying to understand more the finance and so on. At the end of the day, what you will end up doing, working with teams made of of different skills, and they need to be able to communicate and collaborate and to solve the problem.
Interesting. So what would be your, I'm sorry, Candace, go ahead.
No,
I've
no.
hogged the mic the whole time.
I genuinely didn't have something to say. I just was absorbing. Please continue. Go ahead.
What's your advice for people today that are in school, whether they're in physics, whether they're in engineering, whether they're in comp sci, marketing, et cetera? Like what would be your advice to someone who wants to get into get ready for the quantum shift?
Like you call it, it's a quantum shift. It's moving fast. It's changing, depending on the the interest and so on. I think the idea of, I think what the most valuable in this evolving time, because we're talking about things that are changing every day, whether it's an algorithm, whether it's in hardware, whether it's technology and so on. I would say the best thing I would do is to join any team that can offer the opportunity of looking at quantum technology from different perspectives, whether from the algorithm side, whether from the hardware side. Doesn't mean you need to work on both, but you have that possibility of interacting. I think that would be the best when it comes to building the actual quantum machines in the future. So the ability to see you're not just focused on the hardware itself, but also on the interface connecting the hardware and communicating with the hardware. On the application side, I mean, all applications are moving towards quantum computing or quantum, or this new way of doing hybrid quantum computing in the future. And having a better understanding of how we are building these quantum algorithms will be a huge plus. It will be as important as learning your analysis and algebra to solve some of your engineering problems. That's how we are going. That's what we are moving forward to. So it will be a tool. You need to understand it, get comfortable with it, and of course you need to understand the application that you're developing and so on. So it's so having that one answer, I don't think it's it's possible. But for any fresh engineer, I would say, for any young engineer, I would say, try to understand your application as much as possible and try to think of quantum algorithms, quantum optimization, quantum computing as an important tool that you need now to master, and you will use it. Because think about it, in the future, all of these quantum computing companies, when their machines are ready, they will say, okay, here we go. Now the machines, go ahead and use them. You can do so much. You need to be ready by then. You have the software, you have the application, you understand how you can run your application, your problem on that type of machine. So it's very dynamic.
Interesting. We're almost at time. And any other recommendations you would give, or Candace, do you have a question?
He gave advice to our listeners on what they should think about considering and how they need to get involved. That's always usually the basis of my questions that I like to ask. I asked him for his thoughts on the future as well. So I'm going to say right now, I feel like we've gotten a lot of great advice and information. So I'm going to say no. Do you have anything that you'd like to ask right now?
I mean, I asked all the questions. I mean, we could probably go on for another couple of hours, but but I think it's interesting to get, you've been in, if you looking at your resume on LinkedIn and whatnot, like you've been in doing quantum or quantum networking for quite some time. So it's good to get your perspective, which I think has probably been one of the most grounded conversations we have. Like, this is, don't get, it's very grounded, right? Because it's the boring stuff, windmill arrangement, right? Very critical, right? These windmill farms, they're massive. They're not insignificant amounts of money are being put on the line, but it helps. You can get the most out of it. And I think that's really, it's the optimization problems, right? It's not that are going to really, I think, make the most waves for business. And those are not going to be glamorous, cure cancer, figure out protein folding, photosynthesis, and all that sort of thing, and optimize that. But I mean, those types of problems, I think, are going to be crucial towards solving a lot of these intractable problems.
Correct. The learning part of it, absolutely. What we are really, yes, the problem may sound boring when you think of new drug and new discovery, but the basis and the learning is actually helping us slowly getting into a
Right.
way better, much better understanding of how things work and what we need to do better and so on. And just like we did, we started working on wind over the last couple of years, we've been working on grid, transferring that knowledge, the idea of the ability to solve these complex problems and so on. And I think this is the, like you said, maybe it's first, these are problems we need to solve. They're very critical today, especially the grid. So what happens in the blackout that happens in Spain recently and in Greece and southern France, and and maybe I should say one thing about this. One of the biggest machines we've built as humans is the electric power grid infrastructure. It's huge, it's complex, and we are reaching a point, and we kept growing it every year. We kept growing it, and we reached the point today that we cannot manage it using even our supercomputers. This is a serious problem today. We built a machine that we are barely maintaining using classical, and we need to rethink our tools. We need to rethink the way we manage it and we solve it. And
Right.
here we go. These techniques, this different way of looking at problems, the way we're navigating the space of possibilities. Like I said, it's a bunch of switches. You need to know which one. You're not going to just turn on and off randomly. Absolutely not.
Right.
So you need to be a little bit more sophisticated. And that's what this new way of thinking of quantum optimization and the way you're dealing it and solving it will be the answer for that.
Interesting. That's awesome. So we want to be respectful of your time, and thanks for coming on the show.
Thanks,
And where can folks find out more about you and your company?
Yeah, so QubitEngineering.com, that's our website. Please reach out. You can find me on LinkedIn too. We're happy to answer any questions, collaborate, connect, and yeah.
Excellent.
Fantastic.
All right. And we'll let our AI finish the show.
And there you have it, quantum optimization, wind turbines, power grids, and a healthy dose of reality from Marouane Salhi. We've journeyed from theoretical physics to practical engineering without so much as collapsing a single wave function. If today's conversation has shown us anything, it's that quantum isn't just about the future, it's about rethinking the present. Whether you're a physicist, an engineer, or someone who just enjoys saying quantum at dinner parties, there's a place for you in this evolving landscape. Be sure to visit QubitEngineering.com to learn more about the work Marouane and his team are doing. And as always, if you enjoyed the show, subscribe, leave a review, or shout superposition into the void, we'll hear it. Until next time, stay curious, stay coherent. And remember, in the quantum world, even boring can be revolutionary.